Welcome back. Today we're going to venture away from the digital world and into the dark and mysterious analog world. Those of you that have had 438 are going to find this really boring because this is what a computer scientist needs to know about op amps. Nevertheless, if you haven't had 438, I think this is a good portion of the class that will give you a tool to go in your toolbox, because I think fundamentally the difference between a good embedded system engineer and an excellent embedded system engineer, the thing that's going to get you to keep the job when there's a reduction in force in your job and you want to keep your job, they're going to let go of the guy who only knows how to program or only knows digital stuff, and they're going to keep the person who knows all the good digital stuff and all the good programming, but is at least mildly effective in their analog skills. And so we're going to do a little bit of analog here in 445L, just so that when there is a reduction in force in your first, second, or third job, we can weather that storm. And that's the same thing as if you're the boss and you have to fire people. Fire people with one skill and keep the people with multiple skills. And so 445L students go kicking and screaming into this part of the class, okay? Because I thought I signed up for a computer class. What are you talking about op amps for? And that is because embedded systems are just that, they're systems, and therefore, and there's a big section in the book. The op amp that we're going to use in this particular class is the OP2350. There's no particular reason we use it except TI sent me a rail of 100 that'll last me all semester, all year. And so this is an op amp we're going to pass out on Friday as part of your need to do Lab 9. Okay? And op amps, you might have seen it with 3 pins. If you add the power pins and the other power pin, which we're going to connect to ground, there you got 5 pins. And this is actually an 8-pin. This is an 8-pin dip, and so we actually it's going to be what's called a dual op amp. So those are the 8 pins that we're going to see here in Lab 9. So when you get the package, it'll actually have 2 op amps on it. There are a couple of wonderful features. We're going to call this VY. We're going to call that VX. We're going to call this VOut. Okay? And again, computer scientist rules to op amps. Okay? Rule number 1. Okay? And that is negative feedback. Okay? In order to make this stable, in order to make this work, we are always going. We will always use negative feedback, okay? And that is done by placing a resistor from the negative terminal to the output. Okay, so that's rule number 1. Now there will be a class of circuits when we get to Lab 10 that uses positive feedback, but it won't be a linear amplifier. So today we're talking about using the op amp in a linear mode as an amplifier or as a filter. Okay? All right, that's rule number 1. Rule number 2 is the fact that this is called rail to rail. Okay? And this, the general rule about op amps is these voltages, all 5 of these voltages, all 5 of those voltages must be between the voltage terminals that I've powered it up with. Okay? So if you happen to get some negative voltages on any of these pins, it's not going to work. It's going to clip. It's going to blow up. It's going to be bad. Or if it goes above 3 volts, it's going to be bad. Okay? It won't work. It'll clip. Okay? Rule number 3 is because of the feedback and because of the rule number 2, it turns out that these 2 voltages are approximately equal. Now, they're not exactly equal. They're off by a little bit because the way this op amp works is V out is going to be equal to some very large number, 200,000, some very large number. That's called the open loop gain, times the difference between Vx and Vy. So if you do the math on that, if V out is between 0 to 3 volts, okay, and it's running in a linear fashion, that's a linear equation. You see that? That's a linear equation. In order for that equation to be linear and for the output to be less than 3 volts, 3.3 volts, then those two terminals, okay, these two guys here must be approximately equal. And that's what the negative feedback will do. Okay, I got one more rule. How about we do next rule number 4 in green. Can you see the green? Now let's make rule number 4 in blue. Okay. Okay. And that is, from an ideal standpoint, from a computer scientist thought about op amps, okay, the current into the two terminals, okay, is going to be approximately equal. Not equal to each other, but they're both going to be equal to 0. Okay? So that's rule number 4. Okay? So the op amp itself, the current here, this IY, and this IX. Now, the actual impedance to this device is either in the megohms or the gigohms, depending upon the technology. But suffice it to say, large enough such that we will assume that the input currents are effectively 0. Okay? Questions on that? All right, so let's do an amplifier. Clear. Okay, blue. It turns out you may have seen this amplifier before. Okay, if this is the feedback resistor and this is the input resistor, this output is negative VF RF or RI times VN. But this circuit doesn't work. Violates rule number 2. Well, I don't care what the number is, but what rule did I violate? The rail-to-rail rule, right? Because it doesn't matter whether if Vn is positive, then V out is negative. Or Vn were negative, V out would be positive. There's no way to make both Vn and V out equal to each other unless the gain is 0, in which case nobody cares. Right? So this we can't build. Okay, we cannot build this. This is not a buildable op amp. And so we'll talk about how to change this into a gain which is buildable in a few moments. Okay, but let's start with a simple one that is buildable. Okay, and that's the positive gain amplifier, blue. Okay. Call this R2. Okay. This one we can build. Okay. All right. Rule number 1. Okay. What was rule number 1? Help me. Negative feedback. We got rule number 1 done? Somebody see it? Rule number 1. Negative feedback. What was rule number 2? It's rail to rail, which that means that we're going to have to make sure. What can you tell me about Vn? Rule number 2 tells me what? That Vn better be between 0 and 3. That's rule number 2. How about what's rule number 3? I wrote it down. What's rule number 3? The voltages at the inputs are approximately equal. So when I analyze this circuit, okay, I know that this voltage here is not connected to or shorted together to, but it is going to be approximately equal to Vn. That's just the rule. Okay. All right, now we need rule number 4. What's rule number 4? It's such a high input impedance that there's no current, right? There's no current here. And no current there either, right? There's no current to the inputs. All right, so now all I need to do to figure out how this works is Ohm's law, right? So now I just use Ohm's law. And I look at let's say I'm going to look at the current through R2. V out minus Vn over R2. Okay, that's Ohm's law. Is equal to Vn over R1. And now we need 9th grade algebra. Right? Now we need 9th grade algebra. V out equals 1 plus, okay, R2 over R1 times Vn. So it's a positive gain amplifier. Okay. You with me? All right. We can relax some of the rules and think about a non, what would an electrical engineer do with an op amp? And that is, we can look at the behavior of our circuits. So if I build a circuit here and I have an input voltage, this is a module, okay? I may be interested in the amount of current flows, okay? And so I am going to define the input impedance as the input voltage divided by the input current. Okay? And we saw for the particular circuit I just made, right, for this guy here, right, a gain 10 amplifier, that the input impedance is what? Okay. The input impedance of this circuit as a performance measure for amplifier goodness, right? It's got a gain of 10, right? R1 plus R9K over 1K. What's its input impedance? Okay, well, if the input were 1 volt, well, it can't be 1 volt because the output would be 10 volts. But if the input were 0.1 volt, right, and the output would then be 1 volt, what is the current? There's a rule about that, remember? That was rule number 4. What current am I going to have? 0. So it's going to have infinite input impedance. This is a perfect amplifier. But turns out it's not going to be infinite. We're going to look at the current. We're going to look inside the op amp and look at the actual current. It'll be on the order of either microamps or picoamps, depending on, it'll either be in microamps or picoamps, depending on the technology. So it's going to be very large. Okay. Let's look at another one. Let's look at the output impedance. The way we're going to model output impedance is to take a beautiful, perfect, ideal power supply and add a series resistance to it, and that will be the definition of our output impedance. This definition, to calculate this, if I gave you such a box, how would you figure it out, by the way? if I just gave, here's a thing, and I asked you to measure its output impedance, what would you do?
Open circuit voltage.
I can open circuit voltage. So what I'm going to do is I'm going to leave it open, okay, and look at the output without it connected to anything. All right? See that? Without it connecting to anything. That's step number one. That's not enough, right? Because I got to do the math. Right? What other thing do I have to measure? I got to measure a current, right? Because so how do I? There's no current if it's open, right? I'm going to short circuit. I'm going to virtually. You don't have to do it on your real chip because that'll blow it up, by the way. But I'm going to short it and then measure the short circuit current. Okay, and that's the definition of output impedance. Op amps will have negative feedback. With negative feedback, this calculation is going to be on the order of milliohms. Okay, really low. But how does this matter? Give me an example where this actually mattered so far. In 445L, yeah, I didn't make you calculate it, but this was actually an important parameter for one of the circuits you built. The output impedance. Okay, so far, where was the largest current you ever created in labs 1 through 5, by the way?
5.
The largest current in what component occurred in this class at this point? The speaker current. So it turns out the output impedance of that amplifier was good enough to drive that 8 ohm or 32 ohm speaker. Okay, so the specification of the audio amp, the goodness of an audio amp with its negative feedback is actually the output impedance. Okay? The ability to drive a low impedance load. We're going to see another one when we get to lab 10 where we drive the motor. But motors and speakers are the places where we need a lot of current. Whereas everything else, the DAC, the LCD, all that other stuff, that didn't matter. This is a slide out of the book. Again, I didn't tell you. I told you we were using an OP2350. And here are some of the non-ideal parameters associated with op amps. You remember I said that there was a gain, and you think about what the definition of a decibel is. Okay, so let's go ahead and define that. Alt-tab, Control-Z. Okay, and so a gain, right? So we're going to calculate the gain in decibels. Now this, remember the rule about log? Log 10, there was 2 rules associated with log 10 you got to remember for the rest of your life. Whenever you see a decibel and you see a log 10 in there, there's 2 fundamental rules that you must always think when someone else is showing it to you, you got to verify it. When you're using it, you got to think about it. The first has to do with whether that's a 10 or a 20 right there. Right? When do I use 10 and when do I use 20? 10 is used for what? Yeah, 10 is used for power. Yeah, totally. Yeah. 10 is used for power. I'm going to use 20. And when do I use 20? Voltage, right? And so I'm going to talk about the gain in voltage. So this is going to be a 20. And what's the second rule? And this is a 10th grade science teacher rule. Units. What are the units on the inside of the logarithm? What's the units of this bad boy right in here? It has to be dimensionless. Okay? So it's going to be V out over V in. Okay? It's going to be a gain. Okay? And that's exactly the gain we were talking about. That V out is some gain times Vy minus Vx. Okay, so this is going to be the decibels 20 log 10 of G. Okay, that's where that came from. Okay, because sometimes they give you a parameter, right? They give you a parameter in decibels, and you got to figure out what that really means. You remember we talked about the input impedance? Okay, the input impedance of this particular op amp is pretty large. Do you know what 10 to the 13th is? You got an ohm meter, right? Everybody own an ohm meter? Right. Not the My Rio, but a real ohm meter. Somebody owns one. Yeah. So what are the dials? What are the impedance dials on your ohm meter? Ohms, right? You got ohms. What else you got? Click. Kilo ohms. One more click. Meg ohms. Okay. Right? 1, 10 to the 3rd, 10 to the 6th. Okay. Where on your dial is 10 to the, that's like 10 teraohms. Okay. No, there's no T spot on your ohm meter. Don't try to measure that. It's so large you can't really measure it. That's the essence of the rule number 4, by the way. Right? Remember rule number 4? Rule number 4 is what? No current in there. Well, that's because you got to drive current into a 10 to the 13 ohm load. Okay? Just saying. It's pretty large. Can't get in there. Offset voltage. Okay, this is matters if you have a lot of okay, not caps. Oh, tap. Okay. The theoretical. There's your op amp. Okay. Blue. You can think of a real op amp, the red one, sort of embracing a ideal op amp, the blue one, and the offset voltage is the actual voltage that if you put at the inputs of your op amp, that would give you a 0 output. Okay, that's what offset voltage is, and we're basically going to so if I have a gain, let's say if I have a gain of 10, that offset voltage is going to create an output error, offset error of 5 millivolts. See that? That's a consequence of that. So whatever you thought you had, you're going to get 5 more. If you have a gain of 10 amplifier, you're going to have 5 more. If you had a gain 100 amplifier, now you got 50 millivolts. Okay? And so if I asked you on the test, how do I reduce the effect? Well, first of all, what is the effect of an offset voltage? I asked that question on the test. What would be the answer? Offset voltage causes an offset at the output of the value equal to the offset parameter times the gain of the circuit. Okay? So, and then the second question I would ask you is, how do you reduce the offset error? It has to do with the columns. Look at the columns on this. What if I decided to use a TLC 2272? What would happen to my offset error? I get worse. That's not good. What if I decided to use a max 492? It would be the same. But if I wanted to reduce the offset error, what would I do? Use the other one. Yeah, use this one here. Okay, where'd it go? 50 microvolts. Okay? That's the consequence of this. Let's do one more that's important, and let's do frequency response. Okay. All right, so this is an amplifier. With gain 10. Okay? This is an amplifier with gain 10 at DC. Now you put in 0.1, you get 1. You put in 0.2, you get 2. Right? Gain 10. But something bad happens. At higher frequencies. It stops working. Yeah, just get over it. It just does. At some point, it stops being an amplifier. It won't pass a terahertz. It won't pass whatever 10 times a terahertz are. At some point, it'll stop working. And in that formula, if this were an OPA 2350, we could find that cutoff, the point where this drops down to minus 3 dB, from this table. Okay, and that's this guy right there. Okay, that's telling me that the gain times the bandwidth is going to be a 38 megahertz. So this tells me in this figure here that this number here is 3.8 megahertz. Because the gain was 10, and I used a 38 megahertz amplifier. Okay. At that point, it stops being an amplifier. So if this were your audio circuit, well, okay, you can't pass sound over 38 megahertz. Okay, but you remember your audio circuits from before. Remember our audio circuits? We showed an audio circuit. Remember what the gain was on our audio circuit? In the previous, we talked about the electret. I had a gain of what? I had a gain of 100. Okay? So if this gain, right, if this gain were 100, what would be the effect? Right? What would be the effect of this plot? What would happen if I increase the gain? What's going to happen if I increase the gain in this circuit? So I wanted 100, I didn't want 10.
Frequency will increase.
No, I didn't increase. Look at the formula. Okay, look at the formula. Okay? The gain times the bandwidth is a constant. So if I increase the gain, what's going to happen? It's going to decrease. So the rule is the gain times the bandwidth, FC, of the circuit is equal to 38 megahertz. That's the rule. So this is going to drop down to 380 kilohertz. Okay. All right, so now I asked the question on the test. What if I wanted more? I want it faster. Okay, turns out I already chose you the fastest one. See that? Which may be the reason I chose it, because speed guy, I want it fast. But I bet you can find it. Let me teach you one more fundamental thing about speed. And not that speed kills. That's a defensive driving question. Okay, what does speed do in embedded systems in electrical engineering? Takes more power. Okay, so you can actually see it from here. If you compared the power down here, right? Compare the amount of supply current, okay, down there, you'll see that it's linearly related to how fast it is. Okay? Now, if I change technologies, we get a new curve. But if I take the same technology, the same integrated circuit technology, and I span it across the speeds, I'm going to get pretty straight line between the power I times V and the speed. All right, so that's enough of that. Sometimes our problem looks like this, where we have a ground, but the input is not one wire, but two wires. And the previous thing we had, like the electret microphone, had a single voltage, and the sound was on that single voltage. But sometimes the information is on the difference between two. Okay? So this is called a differential amplifier. Okay? A differential amplifier. If I were to actually build one, I could do it this way. And it turns out I'm going to use the same R1 and R2. And this is my input now. And there's my output. If I were to build this, let's go through the rules. Rule number 1, is there negative feedback? Yeah, you see it right there. Rule number 1. There's negative feedback. That's this guy. Okay. Rule number 2. Right, there's no, I don't remember the rule number 2. There's all the numbers are less than 0 to 3. So that tells me that V1, this guy here, and that guy, and this guy, all have to be positive. Okay? So that tells me something about Vin. Right? Vin has to be positive in order for this to work. Right? Because Vout's got to be positive. Okay? Let's see what else I can see from this. No current into here, right? So if I call this guy V1, okay, what voltage is right here? What voltage is right there? Right? You see that? R2 over R1 plus R2 times V1. Okay, and the rule says what? That's equal to this, right? So this voltage here is also R2 V1 over R1 plus R2. Okay. One more Ohm's law. Okay, right? If I can do Ohm's law through, I do Ohm's law through this pair right there, right? And I call this V2. Ohm's law through there. And then I do the math. I'm going to get something like V out equals R2 over R1 times V1 minus V2. Right? It's a differential amplifier. Okay. See that? And this, I skipped a lot of math, but I promise you it's no more than 9th grade algebra to get from the 4 fundamental principles of this amplifier to this very simple thing. Okay? And if I have a gain of, let's say this ratio here is a gain of 100, right? So this output is 100 times that difference. That tells me that this difference here has to be less than whatever, 3.3 volts divided by 100. Okay? In order for this thing not to saturate. So I'm going to take a small signal and differentially amplify it. Okay? And there's a couple of definitions associated with differential amplifiers, and that is the common mode impedance is if I take those two inputs right here, this was my V1 and that was my V2, and I short them together, the output should have gone to 0, right? Should have. Okay. And then I look at the current that goes in. That's called the common mode impedance. If I connect an input in this way and I look at the current, that's called the differential mode impedance. This is really important for things like EKGs and thermocouples, and it turns out that these two parameters here have to do with how much I'm going to load down. Okay. So if I have a module here, okay, how did I model the output? What was my model for the output of a module? A ideal voltage source and what?
Resistor.
And a resistor. When that resistor had a name, remember the name of that resistor? That's the output impedance. Okay. how could I model the input of a module with an input impedance? Okay. And then I'm going to connect them. Okay. Now, I'm not comparing the input impedance of a module to the output impedance of that same module, right? I'm comparing the output impedance of A with the input impedance of B, assuming A is connected to B. So when I'm transferring voltage from one to the other, this is going to give me a design parameter that says I want the input impedance to be larger than the output impedance. But remember, this is 445L, and let me just give you a definition of much, much greater than, okay, by the way. And I'm going to define this ratio here. Yeah, I get that right. Again, this is the input impedance of B compared to the output impedance of A. Okay? That this has to be bigger than 2 to the n, where n is the number of bits in your ADC. Because I want the error to be inconsequential as measured by the analog to digital converter. That's how I'm going to specify the parameters here. Okay? And so this is going to be a function, because if you look at it, any voltage difference across here does what? A voltage drop in that resistor means what? So this is the correct signal here. And I don't want it to change. I want to sense it. So I want to have a large input impedance connected to a small output impedance. Those of you that are real electrical engineers, there's another parameter, another problem, another configuration where I'm trying to transfer power or energy. If I'm going to transmit energy between module A and B, what do? This will not be on the test, but it might be on life. If I have two modules and I want to transfer energy from A to B, like I'm trying to get electrical power from Houston to Austin, right, across a distance, what do I do with the impedances? I make them the same, it turns out. But we don't ever do that, because that's for transferring power. We're going to do it this way. All right. We're going to transfer voltage. I'm going to have one more rule, okay, just to recap. Okay. Okay. Is we had negative feedback. That makes it, why is that good, by the way? It's a beautiful thing. Here's my analogy. Take a pen, okay? Take a pen and try to balance it on your finger. Brave person. Try it. Try to pencil. Try to balance it. Yeah. Losers! Try it. Let go. Can't do it. That's positive feedback. Okay? Any scoundrels out there? Balanced. This works wonderfully. Negative feedback. Any deviation from straight down is going to cause a force to cause it to become more stable. Yeah. Negative feedback. Awesome. Positive feedback. Hard. Yeah, this way is hard. This way is easy. Okay? That's rule number one. Just saying. Okay? It's rail to rail, which means all of my signals got to be between 0 and 3.3. It actually doesn't work quite perfectly near 0 or near 3.3. So, make them go from 0.1 to 3.2. If you want to sort of sub-rule to that. Okay, it works a little bit better if I go further away. Let's see, what was the next rule? Use the same order. No current. Yeah, no current. In, okay, and the output I got them out of order, sorry. That the two op-amp inputs are approximately equal. Okay, so I'm going to add one more, and that is when you come to my office and you're looking for resistors, you're going to find a lot of them from 1K to 1 megohm. Don't try this with 100 megohm resistors. It gets weird. Don't try it with 50 ohms. It gets weird. So we're going to have resistors in the range from about 1,000 to 1 million. All right. Okay. So that's my fifth rule. Okay. You want to press somebody in an interview, or you want to do the exam question 2 in a very quick way. Okay? I'm going to use all of these rules in 4 easy steps. Okay. So V out. Okay. So give me a number between 1 and 5. Just so you can believe that I didn't fake this. Number between 1 and 5. 4. Oh, the number could be negative too, by the way. Okay? 0 is kind of stupid, but between 1 and 5, give me another number. Negative 3. Now give me one more number. Make it 1.5. Sorry. Well, it could have been any other number. You're fine. Come on, give me a number. I can do it. Race. Give me a number between plus and minus 5. But not too many digits, because I got an integer number between 1 and 5. 2. Yeah, that's not too bad. 2. I can cheat. 2 will be no trouble. I can cheat. Yeah, that's good. Okay. All right. I start with any problem, with any numbers in there. I can have as many digits as I want. Okay. I'm going to first choose a reference. Okay. So if I choose a V reference from your LM2024, right? Let's say I have I choose it to be 2 volts. That's why I knew I could cheat. Right. So I'm going to rewrite this: 4V1 minus 3V2 plus VR, V reference. Okay? There we go. The next step is to add some ground gain such that the sum of 4 minus 3 plus 1 plus whatever number I put right there is equal to 0. So I got right now I've got a 2, right? You see that? I'm up to 2. And I want to go down by 1, so I'm going to go minus VG, where VG is ground. Okay. The next step, not 0. It's got to be 1. Sorry. The rule is erase. It's got to equal 1. Okay. The next step is to find a common multiple of all of those, like 12, right? 12. All right, so now we're ready to build a circuit. I need negative feedback, so I'm going to choose a resistor which has a 12 in it, and 120K fits in my range. Okay, V1 needs to be a gain of 4. So I'm going to divide 120 by 4. I'm going to make this 30K. V2 is negative, so it's going to come in down here. Okay. It's got a gain of 3, so this ratio's got to be 3, so that's 40K. V reference has got a positive, but it's got a gain of 1. So that's 120K. See, that ratio is 120. I got one more. I got a ground. Right there with a ratio of 1. It's negative because it comes in the negative terminal. 120K, ta-da, I'm done. This process, this 4-step process of adding a reference, adding a ground, so it sums to 1, and then putting in the positive gains on the positive side, putting in the negative gains on the negative side, choosing a resistor which is a common multiple of all the gains, will work for any circuit. Any linear combination of any number of inputs to get me my output. All right. I'm done. All right. So what have we learned? We've learned how to make op amps give gain. Right? We talked about V out equals some constant times V in. We learned about the differential. And then we learned a third way, which was a general purpose way to do an op amp. What's next is to use the op amps to make analog filters. Okay? So that's what we're going to do next time. We're going to do analog filters, and we'll create. So we saw gain. Okay, the parameters that we dealt with the input impedance, the output impedance, and the bandwidth. Okay, those were the things we were interested in. We had our rules. We wanted input impedance, output impedance, and bandwidth. We saw about how to make it better. Right, spend more money on your op amp. Dump more power into it. Okay, use some power speed. All right, question.
If you wanted to make the reference voltage, would you need one of those diodes?
Yeah, Anupes, how do you make a reference signal? And that's there's lots of ways you can buy it, or as we saw, we made our references with 3 resistors and the shunt diode. Okay, the LM4041. That's how we're going to do it in this semester because you already got that part. It's not the best reference. Spend more money and better reference. Any other questions? That was a good question.